This is the first question from the magnetism practice packet. It's the second question on the 2007 alternate exam. It reads, a beam of particles with charge positive 3.2 times 10 to the negative 19 coulombs. Of course, that's going to be important just because we should recognize that the polarity of the charge is going to affect its results in a magnetic field. And mass 6.68 times 10 to the negative 26 kilogram enters region 1 with a range of velocities all in the direction shown in the diagram to the right. There's a magnetic field in the region 1 directed into the page with magnitude 0.12 Tesla. Charged metal plates are placed in appropriate location to create a uniform magnetic field of 4,800 newtons per coulomb, which is in region 1. So you have two fields. You have a magnetic field directed into the paper, and you have an electric field. We haven't quite figured out that direction yet, which is essentially what they're asking in part 1 here. So they say on the diagram, sketch electric field lines in region number 1. First of all, let's recognize that that each one of the particles that enters the field is positively charged. So they say that it passes through region 1 undeflected. That, of course, being very important. So here's the velocity vector through region 1. So if it's moving to the right and it's positive, we're going to use our right-hand rule. We're going to put our middle finger into the paper in the direction of the magnetic field. Our index finger goes in the direction of the velocity, which is to the right, and therefore our thumb points in the direction of the force acting on each one of these particles. And so you should recognize then that the direction of the force acting on the particles magnetically must be up, which then means that the electric field must be directed downward in order to counter it. So again, the direction of the magnetic force is up. The electric field force, on the other hand, must be directed downward if it in fact remains undeflected through region number 1. So I've gone ahead and sketched that in. I'm going to label that electric field. It is a vector, so I need its vector hat. So the electric field is directed downward on the paper. The second question goes on to say to calculate the speed of the particles that pass through region number 1. If they pass through undeflected, we should recognize that the sum of the forces is equal to 0. Let's go ahead and draw just a quick free body diagram off to the side. We should realize that on a positively charged particle, there is an electric field force directed downward and a magnetic field force directed upwards. The sum of those two forces is 0. They are equal magnitude but opposite in direction. And that's going to help me write my dynamics equation, which is essentially going to be that the upwards electric field force, magnetic field force minus the electric field force directed downward is 0, and therefore I can say that F sub B, or the electric field force, is equal, the magnetic field force is equal to the electric field force. Once I've arrived here, I can now substitute in for the magnetic field force. Of course, I'm going to use QVB, and I'm going to use sine theta. Let's remember that the trig piece here, theta, is going to be 90 degrees, and so ultimately that's going to be equal to 1, everything here in the brackets. So I can ignore that since I know that they're at right angles to each other. And the electric field, by definition, I'm going to kind of write this off to the side, and I'll choose a different color. The electric field is described as force per unit charge. And so therefore I can describe the electric field force, F sub E, as the strength of the electric field in newtons per coulomb, E times Q. And that's exactly what I'm going to do. I'm going to substitute that in right here, E times Q. So immediately now I can see that these the charges cancel out, and they want to have me solve for V. So I'm going to divide both sides by B, which is given to me here in the problem, the magnitude of the magnetic field. So then when I'm solving for V, I'm going to get an expression that looks like this, assuming that this is 1, and I'll basically just leave it there. I'm going to get E over B. And at that point, I'm ready to substitute. So I'm just going to plug these numbers in. I'm going to put in for the electric field 4,800 newtons per coulomb. And for the magnetic field, I'm going to put in 0.12 Tesla, and therefore I get a speed of 4 times 10 to the 4th meters per second. That's going to be my answer for part 2. Okay, so now I'm ready to move on to the next question. The next question says the particles that pass through the center region 2, in which there is no electric field, the magnitude has the same, so it's still 0.12 Tesla. The path of the particles in region 2 is a circular arc of radius r. They want us to calculate the radius r. So immediately I see now that we've got some circular motion. I'm going to remember back from dynamics and UCM that a centripetal force is equal to mv squared over r. Once that positively charged particle enters region 2, there is only an upwards magnetic force acting on it. And the magnetic force is the centripetal force. That's the only force acting on the particle, which is why it moves in a circle. And so basically, I'm going to use this expression to move forward. So now I can say that QVB, again sine theta, I'm being kind of more formal here, is equal to mv squared over r. So now I know the magnetic field force is equal to the centripetal force. Let's go ahead and work with this thing. We're solving for c, the speed of the particles, so I know I'm going to be solving for v. One of those v's, that v cancels out with one of these v's on the right-hand side. And that's it. They want me to, not calculate r, v, they want me to calculate r. So I'm going to multiply r both sides of the equation. And on the right-hand side, I get mv, and then I get a divide by q and b on the left-hand side, and then I get an expression that looks like this. The radius of the curvature is equal to the mass of the particle times its speed divided by the magnitude of its charge and the magnetic field. And at that point, I'm ready to plug everything in. The mass of the particles were given to me in the problem as 6.68 times 10 to the negative 26 kg, and I'm going to multiply that by the speed of the particle, which I solved for in the previous problem, 4 times 10 to the 4th meters per second. Those are the ones that make it into region 2 undeflected in region 1, that is. The charge is 3.2 positive, 3.2 times 10 to the negative 19 coulombs. And I'm going to multiply that by the magnitude of the magnetic field, which is going to be 0.12 Tesla. Once I put all of that through my calculator, I turn the crank and I get 7 centimeters, or 0.07 meters, which is my answer to part B of that first question. Okay, the next question then goes on and says, within the beam there are particles moving slower than the speed you calculated in A part 2. In what direction is the net initial force on these particles as they enter region 1? If they're moving slower, then the magnetic force changes. So let's go ahead and draw that. Let's remember, if it's got the same charge, then the upwards electric force, F sub E, is the same, but the magnetic force, F sub B, goes down. So, no, wait a second here. Looks like I got those backwards here. Let's redraw that. The magnetic force is acting upwards. That's where I made the mistake. The magnetic force is acting upwards, which has gotten smaller. The electric force, which is acting downwards, stays the same. And so therefore there's going to be a net force here towards the bottom of the page, since the electric force is going to be greater than the magnetic force as the particle's speed goes down. All right, let's go ahead and move on to this last part of the problem. Part D says, all right, a particle of the same mass and same speed is in region 2, but with a negative charge. As in part A, number 2, but with a negative charge. So basically the only thing that's changed now is the magnitude of the charge is the same, but it's just negative. So now they're saying, hey, make a sketch of what you think is going to happen. So don't get duped. As soon as you see this negative sign here, you should be thinking to yourself, all right, these are the kind of things here that trip me up, so flags should go off. So you got to be careful. Here we're going to draw our electric field lines, which if we go back up to the top of the page, we can see that they're directed down. So the electric field lines are directed down, which means that the electric force on a negative charge is going to be up. in the opposite direction. So I'll just kind of remind myself of that. So the electric force on this negative charge is going to be up. I'm going to use the left-hand rule now since it's a negative charge. My middle finger goes in the direction of the magnetic field into the paper. My index finger goes in the direction of velocity, and now we can see that the magnetic force is going to be acting downwards. So we just basically have a reversal of the magnetic force and the electric force, and then that's it. So basically it passes through region number 1 totally undeflected again, just like it did previously. That should be a straight line, and then we can see that it's going to arc as soon as it enters in region 2, and the reason is the electric force is no longer acting once it gets into region 2, and therefore I have a center-seeking force directed initially downward, but towards the center of the circle, which is going to be somewhere here, as that negative charge basically negotiates the circle.